Hello kiddos. If you guys are working as hard on your Algebra 2 as I'm working on Algebra 2, y'all should just be making some really good progress here. Videos are not particularly interesting, but at least we're going to be able to have some work where you can follow exactly what I'm doing and make some progress. So we're going to go ahead and do section 1.4, which is dealing with quotients of polynomials. But first, what is gray and blue and very big? And that doesn't mean gray hair and blue shirt and very big like me, no. It's an elephant holding its breath. And secondly, what is a kitty cat's most favorite song in the whole world? Three blind mice, which becomes two mice and one mice, and then finally no mice at all. Section 1.4, quotients. We have been working with lots of properties of exponents. Power property, of course now I can't come up with the words right now, the zero property with exponents. What happens when you have the product of two exponential expressions? So now we're going to be talking about one's properties that you use when we're dealing with quotients of exponents. And you'll remember that a quotient is the solution to a division problem. So first off, the very basic property is the quotient property of exponents. Surprise, surprise. Let me put my little mark here. Surprise, surprise. Quotient property of exponents. In other words, how do we handle it when our problem involves the quotient, which is ratio form, of two terms that happen to be exponential expressions? If you have one exponential expression divided by another exponential expression, how does that actually work out, or what's our answer going to be? So let's just look at an example first and see what we might have. So what we have is, let's say that we have, for example, 2 to the 4th divided by 2 squared. Well, we know that 2 to the 4th is 2 times 2 is 4 times 2 is 8 times 2 is 16. That's 16 divided by 4. So we know that we want to end up with an answer, with a solution of 4 to our problem. But let's see how else we might be able to illustrate this. We have this exponential 2 to the 4th. That means we're using 2 as a factor 4 times, correct? What are we dividing that by? Well, we are dividing it by 2 used as a factor 2 times again. Very easy. You know that you can cancel common factors. What do we have left in the numerator? We have 2 times 2 in the numerator, and then of course there's a factor of 1 left in the denominator. So we have 4 over 1, which of course gives us a solution of 4 to our problem, our initial problem, which was 2 to the 4th divided by 2 squared. So how many factors of 2 do we have remaining up here in the numerator? Well, we have 1, 2 factors of 2. 4 minus 2 is equal to 2. I wonder if there's a connection there. Well, what happened if we would say, if we had a problem that we really wouldn't want to work out? 2 to the 7th divided by 2 cubed. Now let's see what 2 to the 7th is. Well, know that 2 to the 2nd is 4 times 2 is 8 times 2 is 16 times 2 is 32 times 2 is 64 times 2, that's 128 divided by 8. Okay? 128 divided by 8 is, 8 goes into 12 one time, 48. 6 8s are 48. I don't like having to solve that problem. That was a little bit uglier. Okay? 2 to the 7th is 7 factors of 2. 2, 3, 4, 5, 6, 7. Perfect example here of how exponentiation is a fast way to show repeated multiplication. 1, 2, 3, 4, 5, 6, 7. 2 cubed uses 2 as a factor 3 times. Cancel common factors. There's 1 pair of 2's, 2 pair of 2's, 3 pair of 2's. 2 times 2 is 4 times 2 is 8 times 2 is 16. And sure enough, how many times is 2 used as a factor here? 2 is used as a factor 4 times, which is the difference of 7 and 3. So that's what our quotient rule tells us for when we're dealing with the quotient of exponentials. If you have a rational expression, x to the a divided by x to the b, that's x to the a minus b. And there's also a condition that goes along with this. There's some time that this problem would cause us some difficulty. Now what happens? Well, this is not one that you'd even really think about, but here we have to say x has to be different from 0. The base has to be different from 0, because it doesn't matter if you have 0 to the 10th power, 0 to the 1st power, 0 to the millionth power. No matter how many times you multiply 0 by itself, you're still going to have 0. So this quotient property holds true any time that you have a base that's different from 0. Well, now let's think about this. What would happen if we had x cubed divided by x to the 5th power? Well, it says, our rule tells us that when we have a ratio of 2 exponential expressions where the base is the same, you keep the base and then you take the exponent of the numerator and you subtract from the exponent of the numerator the exponent of the denominator. So what is x to the 3 minus 5? What's 3 minus 5 equal? What's a negative 2? So this tells us x to the negative 2. Thinking, it's not making a whole lot of sense to me, Miss Betsy, because you told me that when we have an exponent, that you're going to use this base as a factor that many times. How can I use x as a factor negative 2 times? Well, you can't use x as a factor negative 2 times. You can only use it as a factor a positive amount of times. Just like you can't drive negative distance. You know, you drive to church and then you drive back home. It doesn't take those miles off your car. We can't use this as a factor a negative number of times. So let's think about this a little more. Okay, we use the rule that we have up here. X to the a divided by x to the b, no matter what it is, you keep the base, you subtract the exponents. The exponent in the denominator is subtracted from the exponent in the numerator. Well, we did that down here, and that gave us a negative number. And now we don't know how to use x as a factor negative 2 times. So I'm going to go ahead and erase this general form here. And I'm going to put right back up here. X cubed divided by x to the 5th, where we used our quotient property and said that was x to the 3 minus 5, which was x to the minus 2. And now we're saying, what in the world is going on here? Let's look a little bit further. What exactly is it that x cubed divided by x to the fifth is asking us to do? Well, it says that x is used as a factor 3 times in the numerator. And in the denominator, what we have is x used as a factor 5 times. And you can always have a factor of 1 every place. Now you know that from canceling common factors, as long as you have the same factor in the numerator as the denominator, that value is equal to 1. You can cancel it out. Well, so we have 2 pairs of factors, 3 pairs of factors. What do we have left now? Well, we have 1 over x times x, which is x squared, which says that x is used as a factor in the denominator 2 times. So what do we have here? Have something here that's very, 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 very important. When we use our quotient property rule that says when you're taking the ratio of exponentials, you keep the base and you subtract the exponents, but then we end up with a negative exponent here, which doesn't mean anything to us right now at this point. So we're saying, okay, left saying, what am I going to do here? Well, when we actually wrote out factors divided by factors, canceled common factors, we found that we got something that looked different. We got 1 over x squared. Both of these methods of solving this problem are equally legitimate, equally valid factors, which means, equally valid methods, which means that our 2 separate answers are equally valid answers. So what that means is if you have a negative exponent, you can rewrite it as a positive exponent by, see this x to the minus 2 is actually x over a 1. You can move the x, move the base across the fraction bar, and your exponent becomes positive. Or you can also think of this as saying, okay, this is x. What is the reciprocal of x? You have x, which can also be written as 1 over x, right? So the reciprocal of x is 1 over x, because with the reciprocals you turn it on its head. So if the reciprocal of x is 1 over x, when you have a negative exponent, you can rewrite it as that same positive exponent, but using the reciprocal form. That's a little bit strange. Chew on it, figure out how to work it. What you have is the second property that we want to talk about, and this is called the negative exponent property. And this is exactly what I've illustrated to you right here. This is the negative exponent property. This says that if you have a negative exponent, x to the negative a, that can also be written like 1 over x to the positive a, and again, we have to say that x has to be different from 0, or x cannot be equal to 0. So if you have a negative exponent of a base, you write the reciprocal of that base, and the exponent is positive. Similarly, if you had 1 over x to the negative a, 1 over x to the negative a, that would be x to the positive a. If this one is frying your brain too much, just do some practice and it'll make more sense to you. The final one that we want to do is the power of a quotient property. Power of the quotient. Now remember, what did we do when we had the power product? You had this product, 2 times x times y squared. You had that product raised to the 3rd power, and you saw that this exponent had to work on all of these separate factors in here. So it became 2 cubed, x cubed, y squared, raised to the 3rd power. 2 cubed is 8, x cubed, y squared to the 3rd is y to the 5th. This is what you did when you had just the power of a product. But now we want the power of a quotient. What's a quotient? You have x to the a divided by, let me see if they want to do this differently, y. You have a quotient. You have some numerator, and then you have a denominator. And you want to raise that entire quotient, or this entire ratio, to a power. And what is really nice about this is that this acts on the numerator and the denominator similarly to how it does with the power. Okay? Really easy. Let's say that I have 2/3 to the 3rd. The numerator is cubed, and the denominator is cubed. Very easy process to do. You just have to know the rule. So these are what the quotient properties are that you need to review for this section. So we're now on page 20. This says, apply the properties of exponents to simplify the following. So if you have x to the -3, it says if you have a negative exponent, you write the reciprocal of the base, x, the reciprocal is 1 over x, and the exponent's positive. There's no work to do, you simply have to know that rule. Now, if you have, oh my goodness, I don't think I want to do this one this way, but I want to know what is the reciprocal of 1 over x to the -7. Now I just showed you one way to do this. I said we're just going to use the reciprocal of this. We already have 1 over x, so that's going to become x to the +7. Let me show you how they want you to use the rule that they taught you to do this. If you have 1 over x to the 7th, they taught you that x to the -7 can be written as 1 over x to the 7th. See, x to the -3 is 1 over x to the 3rd. X to the -7 becomes 1 over x to the 7th in the denominator and in the numerator. So what is this really asking us to do? This is saying 1 divided by 1 over x to the 7th. How do you divide a fraction? You multiply by the reciprocal. 1 times x to the 7th over 1, which is x to the 7th. chew on this as long as you need to understand what to do with problems like this. Okay? The third example C that they have for you in this example number 1, part C, you have x cubed divided by x to the 5th. What this says is we have a quotient that we're finding. You keep the base, you subtract the exponents is equal to x to the minus 2, correct? But we don't like to have negative exponents. X to the negative 2 becomes 1 over x squared. That's using all of those rules that we just talked about. Now, we have example number 2. Example number 2 says, let's divide 25a cubed bc squared divided by b. Okay, I'm not sure what I was looking at, but it wasn't the right thing. 25a cubed bc squared divided by 5a b cubed c. Make sure when you do these problems that you've gotten them written down correctly. 25a cubed bc squared, 5ab cubed c. 25 divided by 5 is 5, right? How do you divide a cubed over a? Well, that's a to the 3 minus 1, isn't it? You keep the base, subtract the exponents. Now you have b, we want to subtract the exponents. I don't see an exponent with that b, but there's still a factor of b there, so it's b, 1 minus 3, c to the 2 minus 1. Okay? Hang in there, it's really strange sounding, but you can do it. 5a squared, b to the minus 2, c. Okay, now that we're at this point, we want to make sure that all of our exponents are positive. And of course, this right here, this b, has a negative exponent. Now think, this is what all they're actually doing, is if you divide anything by 1, you're not changing its value at all, because if you divide 72 up into one group, you still just have 72. But this makes it look much more obvious to you that you actually have a ratio here, or something that looks like a fraction, something in the numerator, something in the denominator. When you have a negative exponent, simply move that base to the opposite side of the fraction bar, and your exponent becomes positive. We have b to the minus 2, so we're going to move that whole b to the minus 2 across the fraction bar, and it becomes positive. So if we have 5a squared b to the minus 2 c, we're going to put all of our negative exponents on the other side of the fraction bar. And you see, there's no fraction bar there. There isn't, but you can put one there. So that's 5a squared c over b squared. And that's because you can turn any whole number or any single expression that doesn't look like a fraction into a fraction by dividing it by 1. We've moved this b to the minus 2 to the other side of the fraction bar and made it positive. So our solution is 5a squared c divided by b squared. Go through this and through it and look at it, write it out, look at the example in your book until this makes sense to you. Okay, let me go ahead and get the next example. Okay, this is example number 3. What I'm going to do is go ahead and stop this video right here and say this is the end of part 1 of video part 1 for section 1.4. I'll finish part 2, which has 4 more examples on it. That's just to break it up so that you're not totally zoning out on me on this algebra.